Hello and welcome to today's video. Today we are going to talk about line integrals. The setup is this. Consider you have a function and a curve. And let's say that curve maps to the r to the n and the function is defined on r to the n. And of course you could define a function that is defined on just the real interval by evaluating f after that curve. So basically you're restricting f to the curve. The question comes up, can we integrate f along such a curve? And that leads to the notion of what is called line integrals, or integrals of a function along a curve. So to recap, consider a function f. Let's say that's defined on r to the n maps to r. And also a curve, gamma, that's defined on some interval, alpha, beta, and maps to r to the n. Then basically f after gamma is a one-dimensional function. So that is a function defined on the interval alpha beta with values in R. It's the restriction of that function f to the curve gamma. For applications, think of something like f modeling a landscape with hills and mountains, and gamma is your path through that landscape. So f of gamma is the actual path that you take, including that height information. Okay? So that's something like a hiking path through hills and mountains. That could be modeled in that way. And we're interested in the line integral. So the integral of f along that curve, that would be something like the energy you need to spend on that hike. So we would like to compute the integral of f along gamma. And that is what is called the line integral of f along gamma. Now, the idea here is very much like we did with the curve length. Again, we're going to take a curve, we're going to subdivide it into certain intervals, we're going to have a look at the polygonal path, and of course along such a polygonal path we can easily compute an integral. So imagine again we have a curve like that, so that's our curve gamma, and we take points along that curve like this. T0 is going to be alpha. Then we have points in between, T1, T2, and so on. And finally, Tn, T3 here, is equal to the last point on the curve, so that's beta. And then we can just take the polygon here and evaluate f along that polygon, so we can compute a Riemannian sum. Okay. So, in analogy to curve length computation, consider a polygonal path given by some points. T0 is alpha, then is T1, and so on, up to Tn minus 1, Tn, and Tn is equal to beta. Path passes through gamma of T0, gamma of T1, and so on, up to gamma of Tn. Then we can define a Riemann sum along that polygonal path. And basically that looks like this. So we again start with k at 1, sum up to n. The length of that polygonal section, of course, is again important. And we just multiply that with a function value. And for Riemann sums, we can either take lower Riemann sums or upper Riemann sums, or anything in between is actually fine as well. So let's just say we consider a suitable point in that interval. It's not that important which point we choose here, okay? So we choose a point in that interval, evaluate f on that point. So f of gamma of tau k, where again tau k is a point in the interval from tk minus 1 to tk. And let's just say that's suitably chosen to either yield the lower Riemann sum or the upper Riemann sum or anything in between. And then of course we need to multiply that by the length of that section of the polygonal path. So that is the norm of gamma of tk minus gamma of tk minus 1. Okay, so very similar to the usual integration, just that we have this gamma in between. And also for the length of a path, we need to consider the gamma values, not the t values. And then what we are doing is the same thing that we did before. So we somehow sneak in this length of the t intervals, tk minus 1. Again, by just dividing this gamma norm expression, that one here, by tk minus 1. That is again positive real number, so we can just put it into the norm if you want to, or take it out of the norm. And then we multiply by that same expression so that it cancels out. So in fact, we didn't change anything here. And now what we can do again is we can have n go to infinity. We have to make sure that the interval length, the maximum interval length, also goes to 0 during that process. And then this whole thing will converge to an integral expression. So if we make n go to infinity such that the maximum of those tk minus tk minus 1 goes to 0, then this whole expression will converge to an integral. And the integral that we get here is basically the same as before, with the exception that we have this f of gamma of t in front of our expression. Again, this expression here in the norm that converges to the derivative of gamma. And we just integrate over the interval from alpha to beta. And basically that's the idea of how we can evaluate integrals over functions along lines. So we just define it that way. So here's the definition of line integrals. Let f be a function defined on R to the n that maps to R. Let me just stress that this is a scalar function, meaning it has values in R, real values, as opposed to a vector valued function that we'll deal with in one of the next videos. And let gamma be defined on alpha beta on an interval and map 2r to the n be a curve. Then the so-called line integral or path integral of f along gamma is defined in the following way as integral. The notation is for such line integral is integral over f ds. We always use ds here as a notation that shall indicate this is about the length of a curve. So remember, the length of a curve is denoted by s of gamma. That's where ds comes from. And we put the curve here below the integral. So this is the notation for the line integral of f along the curve gamma. And that is defined as the integral from alpha to beta over f of gamma of t multiplied with the norm of gamma dot of t dt. Okay, so just as a note, this ds somewhere stands for the curve length s, so you're integrating over the curve length. That's the idea here. And another thing about notation, something that you'll often see is an integral with a little circle in the middle. That is usually used if the curve is closed, so if the end point and the starting point are the same. If gamma is closed, meaning gamma of alpha equals gamma of beta, we often write, to indicate that, integral of f ds along the curve gamma, and then we draw a little circle here on the integral. That is just an indication that the curve is closed. It's not necessary to do that, but you'll sometimes read that in the literature. So that's why I wanted you to know that. Okay, that's it for today. We're going to see an example of that in one of the upcoming videos, and I'll see you then.